Hi everyone, I am Mohammed Zaifaz, and today we are going to learn co-crystal selection. Let's start with. So as you know that co-former selection is a basic part of the co-crystal engineering, especially in pharmaceutical co-crystal engineering. So if we select suitable co-former, then we will go to um, crystal engineering, co-crystal engineering, in order to gain the suitable co-crystals for further experimentation. So I am Mohammed Zefaz from the Material Chemistry Laboratory of the Islamic University of Bahawalpur. Let's start with, first of all, always choose the right path if you are doing any part of your experimentation and any study. For example, here is a castle and your success lies, as you see the crystal, this crystal is your success. And for this success there are two paths. The one is through these stairs, and other one is climbed from back wall of the castle. So if there is a mention of which path is right and which path is wrong, so you should always choose the right path in order to gain success. Don't try to do shortcut ways, use shortcut ways. Okay. Here is a crystal engineering lab. So this is the picture of frustration that I feel when I'm doing many experimentation on co-crystal formation, because I have a single API and a lot of co-formers. So if we if I try many co-formers with my API and uh, gain nothing, so it means that I'm going to waste my API. So it is a dire need to choose the suitable co-former for your crystal engineering. Let's discuss further. Here is a timeline of the development of the co-former screening and the formation prediction of the multi-component solid forms. Some are hydrogen bond-based molecule methods and some are non-hydrogen based methods. In hydrogen-based methods, hydrogen bond propensity, molecular electrostatic potentials, supramolecular synthon and delta pK rules. And in non-hydrogen bond-based methods, lattice energy, molecular complementarity, hence insolubility parameters, conductor-like screening, model for the real solvents, Cosmo RS, artificial intelligence, and some other novel methods. So we will start with the delta pK rule. As you know that the pK, what is the pK? pK is the negative base logarithm of the acid dissociation constant, which is the K of the solution. So how we can find the Ka and the del pK and the delta pK Ka? This is the ratio between the hydronium ion and deprotonated acid over salt. So delta pK is a negative logarithm of the Ka, as you see the equation here, and the delta pK, pK of the base minus pK of the acids. For example, here is the case study of the pyrimethamine. In pyrimethamine, there is two nitrogens N1 labeled and N3, N1 in green and N3 in red. Here is the pK value of the nitrogen N1, which is 6.94, and N3, which is a 4.60. As you see that the pK value of the N1 is greater than the pK value of the N3. And you know that the atom that has smallest pK value has a greater tendency to accept a proton. The larger pK value has a greatest tendency to donate a proton. So here are some case studies to form the co-crystals of the pyrimethamine with the carbamazepine, theophylline, aspirin, alpha-ketoglutarate acid, saccharin, paracumaric acid, succinamide, and L-isoleucine. Their pK value are mentioned here. Carbamazepine 50.37, theophylline 8.6, and many others. You may say. So we form the co-crystals of 1 mean pyrimethamine, and A, B, C, D mean their respective coformers. 1 plus A means pyrimethamine and carbamazepine, and 1 plus B mean pyrimethamine and theophylline. So here is the type of solvent, methanol used 112. Uh, which type of product forms solvated co-crystals mean one molecule of the ethanol will be there, and their delta pK value is minus 8.43. Up to now, this value is theoretical based, not experimental based. So here are their pK values according to this formula, and you see that here dotted circle of the 1A mean pyrimethamine and carbamazepine, and 1B pyrimethamine and theophylline. Their delta pK value is minus 8.43, and with theophylline delta pK value is minus 1.6. And with other coformer, the delta pK value is in the positive range, 3.46, 4.47, 5.34, and 2.43. And with 1G, I mean succinamide, minus 2.68. So what is the rule of the co-crystal formation, co-crystal screening through delta pK value? If delta pK value is less than 0, it means that co-crystal will be formed, and if delta pK value is greater than 3, the salt will form, and if delta pK value is 0 to 3, this is a region of uncertainty, which means that the co-crystal may be formed or not, and your coformer is suitable or not. According to this criteria, we have three candidates, which carbamazepine, theophylline, and succinamide. With carbamazepine, the value is minus 8.43. With theophylline, value is minus 1.66, and with succinamide, minus 2.63. It means that these three values suggested that the co-crystal will be formed in these cases, and other values are greater than 3, which means that there will not form the co-crystal. And as you see that there is solvated salt, solvated salt, hydrated salt. But with succinamide reaction failed to yield any adduct. We will discuss the reason behind this. And successfully we obtain the co-crystals with uh, carbamazepine and theophylline. And in case of succinamide, uh, the value indicate suggests us that the co-crystal will be formed, but actual uh, reaction failed to yield any adducts. Why? Because there is an internal protonation from the carboxyl group to the amide. So proton transform from OH to NH3, because the delta pK value of this nitrogen is 9.76. And as I say earlier, that the atoms which has a greater pK value has a greater tendency to accept the proton. So that's why co-crystal will not form in case of succinamide. Okay. So, and now question arises here. So how we will get these pk values, pk values of the API and other conformers? So there are many tools, online tools for pk calculation. One of these online calculators, Spark online calculators, and acid dissociation constant. And you can also also get a pk value of conformer through literature survey. So next we will move to the molecular electrostatic potential surfaces. The calculated molecular electrostatic potential generated using the density functional theory DFT in the gas phase are used to identify surface site interactions point and predict electrostatic interactions at the surface of the molecule. Here are some molecules and whose electrostatic potential values are calculated at the different regions. As you see here, the mainly four kind of regions: the red, yellow, green, and blue. But the electrostatic potential values are in the regions of red and in the region of blue. So these are the electrostatic potential values of the different molecules. And from these electrostatic potential values, which are in the region of red and in the region of blue, we will calculate their hydrogen bond parameters, that are alpha i's and the beta j's. The molecular electrostatic potentials were converted into the corresponding hydrogen bond parameters. So here are the hydrogen bond parameters, which are the alpha 2.1, alpha 1 2.5.5, alpha 3 1.9, alpha 4 1.4, and alpha 5 1.0. And similarly their beta values 4.5, 6.4, and many others. And you also see that in one molecule there are these two diagrams are the front back diagram of the same molecule, and in this B in same molecule both alpha and beta values are mentioned here. So what is the alpha? It is a maxima in hydrogen bond donor. It means that alpha 1 5.5, this region of this particular compound is a hydrogen bond donor, and this region of this particular compound is a hydrogen bond acceptor, which is shown by the alpha and beta. So his equation E is equal to minus summation ij's alpha and beta j, and delta E. First of all, we will calculate E values and then delta E. And delta is equal to E Cc, which is a co-crystals, minus and E1 minus M E2. Here is E API minus alpha. We will calculate and we will use the values of highest alpha with highest beta. Mean highest alpha is labeled as a 5.5 and highest beta is labeled as a 6.4, and we will use these alpha 1 of API and beta 1 of API. Similarly, plus alpha 2 of API and alpha 2 of API, beta 2 of API, sorry, and further so on. Similarly, of the coformer minus alpha 1 of the coformer multiplied by beta 1 of coformer plus alpha 2 of coformer and beta 2 of coformer, and so on. And co-crystals minus alpha 1 of API multiplied by beta 1 of coformer plus alpha 2 of coformer plus beta 2 of API, and so on. So when we calculate these particular E's for the particular API and coformer, then we will put all these values in this equation and we will calculate delta E. We can also calculate these hydrogen bond parameters from this equation. So here is some cases of the delta E calculation of the 5-methyl-1,3 benzene diol and the coformer computed using all interaction site availables. So here are coformers that we used with the um, orthanol, and their homomeric summation of the homomeric E value, summation of the heteromeric E value, and their delta E. So in case of butane, the delta is minus 32, and in case of 110 phenanthroline, the delta is minus 20.35. So where the highest delta E values, the coformer that give the highest delta E values will form the co-crystals. And you see that in case of highlighted candidates, uh, uh, these candidates uh, will form the co-crystals, and other will not be successful candidates. But in case of butane, which has the highest delta E values, we will not we were unable to get obtain the co-crystals. So here is a top 20 caffeine coformer calculated one stoichiometry. So in case of caffeine, uh, um, uh, apparently we have the highest delta E values with sulfuric acid and sulfamic acid, but uh, uh, we got the co-crystals with these gray shaded areas. As you see, their delta E values are 12, 11, 9, 8, and so on. So next is the hydrogen bond propensities. The hydrogen bond propensity tool developed at a Cambridge crystallographic data centers and available within the Mercury software. It is used to predict whether a co-crystal would form or not when a particular target molecule was combined with a potential coformer. The hydrogen bond propensity is the probability of formation of specific motif, which is dependent on the relative occurrence of the interaction in the given fitting data. So for hydrogen bond propensities calculation, first of all, we open the Mercury. Here is a interface of the Mercury, and then we will go to the file. Here is a file menu. So when we click file menu, we will got these options, and from these we will click on the sketch molecule. And when we click on the sketch molecule, this interface will be opened, and on this we will draw our molecule. For example, this is my um, candidate API, which is a sulfur methoxypyridazine, and this is my other drug molecule, which is a pyrimethamine. Yes. Uh, these are the some drying tool for drying this molecule. And after drying, we will click on the done, and after that this interface will appear, window will appear. When you got this, and then you will click on the CST material. On CST material, you will see these options, and out of these options you will click on the polymorph assessment and click on the hydrogen bond propensities. And from these hydrogen bond propensities, you will get this screen. Here are the two molecules with their atom labeled, functional group labeled basically. Here is a list of the donors, here is a list of acceptor atoms, and here is a function group. So next you will click on the next, and on this screen you will click on the generate, and when you click on the generate, the process will begin, and when it will be 100%, then you will click on analyze. And when you analyze, uh, here some donors and their functional group and acceptors and their functional group will appear. From this, when you scroll this bar from left to the right, and many true false values will be appeared, and you have to ignore those values who have large number of a large number in false and small number in true. I repeat again. You have to ignore those values who have large number in true bar and false bar and small number in true bar. And then you will click on fit model, on fit model, and after that you will get this screen, and to this screen you get accept and calculate. And when you accept and calculate, the file will be saved automatically, and when you will open this file from your selected location, this document will open, and when you scroll down this document you will get this table, and here is a propensity of different atoms. So here is a propensity of hydrogen, nitrogen 17 and oxygen 27 of the sulfonamide, and the nitrogen 17 of pyrimethamine. So this is a 0.88, and all atoms have their hydrogen bond propensities listed here, and you use these hydrogen bond propensities to calculate their delta propensities. So for example, this is my one which is sulfur methoxypyridazine, and this is a pyrimethamine. So I will use the inhomomeric interaction. I mean, if both molecules are of the same API, then their best propensities between hydrogen of the sulfur methoxypyridazine and the nitrogen of this ring, and similarly hydrogen of this amide group and the oxygen of the sulfonamide group. So you use these propensities of these functional group, best propensities of this functional group. So from table, and the best propensities for these functional group are 0.82. Same in the case of pyrimethamine, and their best propensities of these functional group are 0.67. And also their heteromeric interaction, their heteromeric are best heteromeric propensities are 0.88, and in case of pyrimethamine, by using different functional group. For example, here is the amine functional group of pyrimethamine with the sulfonamide oxygen of the sulfur methoxypyridazine, and here is the another amine of the pyrimethamine and sulfonamide of sulfur methoxypyridazine. But in case of this functional group, their hydrogen bond propensity is 0.88. In case of these functional group, their hydrogen bond propensities are 0.82. So their delta AB best, which means that their heteromeric best heteromeric hydrogen bond propensities minus AA best mean best heteromeric hydrogen bond propensities. And in our case, sulfur methoxypyridazine and pyrimethamine, their hydrogen bond propensities of the heteromeric hydrogen bond propensities are obviously 0.82, 0.88. So 0.88 and minus, in case of both homomeric, 0.82 is the best homomeric hydrogen bond propensity. So 0.88 minus 0.86, which is 0.06, which is greater than 0. If your delta propensities will become greater than 0, it means that your co-crystal will form, and if will be less than 0, this means that your co-crystal will not be formed. So next is molecular complementarity. So there is a detailed description about molecular complementarity. You may read this by pausing this video. And for molecular complementarity, same, you use your mercury, and goes to the CST material, and from CST material goes to co-crystal design and screen by molecular complementarity. Here is a 6 parameters. For first one, the fraction of the nitrogen oxygen atoms, and medium and large axis ratio, and small axis, and dipole moment magnitude, and small and large axis ratio. So take all these options and go to next, and from next you will go this. So here is a active. Active means your API, which is a pyrimethamine. Here is a molecule of pyrimethamine, and then goes to select coformer. After coformer, you will open some database in mol to file. So here are some, sorry, um, here are some coformer. So I select alproline and open. Here is a molecule of alproline, and then goes to the next. So this Excel sheet will open. This will tell you about the hit rate 100% and coformer conformation alproline and pass. It means that your co-crystal will form. It means that my with my API, which is a pyrimethamine and alproline, both they form a co-crystal. If this hint may come with not, which means that your co-crystal will not form, not suitable for not formation of co-crystals. So here are the some methods for co-crystal co-former selection. Thank you so much.